Thank you very much. Indeed, I'm going to talk today about semi-definite programs and super resolution problems. So, as far as I know, it's not very close to Stefan's current research interests. However, it's still because of Stefan that I became interested in the field. Indeed, when I met Stefan, he was starting to work on the scattering transform. And when I asked for a PhD subject, he proposed the following question: is it possible to invert the scattering transform? And if yes, how? So the question was, given the scattering transform of a signal, can you reconstruct the signal? And I defended my PhD in 2015, having only studied the question, is it possible to invert the first layer of the scattering transform? Which was already a difficult question. And it turns out that inverting the first layer of the scattering transform is already a non-convex inverse problem, which is an instance of a well-known family of inverse problems, which has been well studied in the literature. And so this motivated me to interest me further in these non-convex inverse problems. And this is what I've studied since. And this is what I'm going to talk about today. So indeed, super resolution is a quite non-convex inverse problem. And so we've studied a specific aspect, at least we have started to investigate a specific aspect of these problems together with Gabriel Perret, whom I guess you know, and with Augustin Cos, who was a postdoc at INS and is now at Université du Littoral Côte d'Opale. So the talk will be in two parts. First, I'm going to discuss the main topic, SDP sketching for super resolution. I'm going to motivate the subject and tell you what we want to do about it. Actually, it's an ongoing work, so there's no theorem. There's a conjecture that we want to prove, and we've worked on it. And in the second part of the talk, I will try to briefly describe a tool that we wrote while trying to prove the conjecture, which is an algorithm to automatically compute integrals which appeared in our computations. So the two parts will be relatively independent. I'm starting with the first one. So I'm considering the simplest example of a super resolution problem. I want to recover a measure on 0, 1. So it's a signal. It's my signal, it's the unknown signal. And so I'm going to assume that the measure that I'm interested in is sparse, meaning that it's a sum of a few Diracks. So it can be written as the sum of Diracks at positions tau s multiplied by weights, as. And the big S will, in all the talk, be the number of Diracks. And to recover this measure, we have access to some linear measurements. We have simply the Fourier coefficients. So we have access to a low-pass filtered version of the measure. For any k, we have the kth Fourier coefficient of the measure for k between minus n and n. N is the cutoff frequency. It's a problem that has already been studied a lot, and several families of algorithms exist. I'm just going to mention the names. They have their own advantages and drawbacks. I don't have the time to discuss them. So some algorithms are based on rewriting the problem in terms of polynomials and using root finding procedures. Others consider directly the optimization problem on the set of measures, and they try to solve it either by semi-definite programming or by directly optimizing on the parameters of the unknown measure, writing it as a sum of Dirac's and optimizing the positions and the weights. So today I'm going to talk about semi-definite programming approaches. The starting point of these approaches is that since sparse measures do not form a convex set, so at least S sparse measures for some fixed S do not form a convex set, a natural approach to reconstruct a sparse measure from linear measurements is to use a convex surrogate. So instead of trying to recover a sparse measure, we try to recover a measure with a small total variation norm. The total variation norm, I haven't written the exact definition here, but in case you don't know it, just imagine that it's the analog for measures of the L1 norm for vectors in compressed sensing. And indeed, if you consider a sparse measure, then it's L1 norm, it's the sum of the magnitude of the weights, so it's indeed very close to the L1 norm. So the story of the talk is as follows. So the original approach is the top part of the slide. So we want to recover this S sparse measure from n Fourier coefficients. We do it through total variation minimization, and it's a theoretically well-grounded approach. There are correctness guarantees saying that the total variation minimizer is, under some conditions, exactly the measure that we want to recover. However, at first sight, solving a TV minimization problem is not completely obvious. But actually, it turns out that TV minimization is equivalent to a semi-definite program and a finite-dimensional semi-definite program. So it provides a feasible numerical algorithm. So this has been known for a while now. Unfortunately, the dimension of the semi-definite program, it scales with the number of measurements, n, and this number of measurements is a priori significantly higher than the number of spikes. So to get over this issue, something that you can try is to subsample the measurements. So people have done it, and they have shown that if you subsample the measurements, so you keep only some subset T of coefficients with a much smaller dimension, smaller size than n, you can still try to solve the problem through TV minimization, and it still works. The correctness guarantees stay more or less the same. And numerically, TV minimization is still equivalent to a semi-definite program. The bad news is that, maybe surprisingly, the dimension of the semi-definite program still scales polynomially with n. And so the size has not been reduced. And to reduce the size of the SDP and hence to get a more computationally tractable algorithm, something you can do is to sketch the semi-definite program. And then we get a semi-definite program with dimension that scales with the number of subsampled measurements, so it's much smaller. However, we don't have an exact equivalence now between TV minimization and the sketched semi-definite program. So this is what I'm going to explain in the first part of my talk, and I'm going to give a conjecture on this almost equivalent part. So I'm starting with the basis. So I want to recover my unknown measure through total variation minimization. So this means that I want to solve the following problem. I want to find the measure whose Fourier coefficients agree with the available measurements and whose total variation norm is minimal. It's been studied around 10 years ago, and it has been shown by notably Candes and Fernandez-Granda. I'm citing here a slightly later result by Fernandez-Granda. It's possible to show that provided that the distance between two spikes in the measure is large enough is of order 1/n, then the total variation minimization approach is correct in the sense that the measure which minimizes the total variation norm is the sparse unknown measure that we wanted to recover. So total variation minimization has correctness guarantees, but observe that the total variation minimization problem is difficult to solve because it's convex, but it's infinite dimensional because the set of measures on the segment 0, 1 is infinite dimensional. So if we want to solve it on your computer, of course we have to discretize or at least do something to make it finite dimensional. And it turns out that this problem is equivalent to a semi-definite program which provides a tractable minimization algorithm. I just want to briefly highlight how you go from total variation minimization to a semi-definite program. So the first step is to compute the dual. And you can see that the dual, I don't have the time to provide the exact derivation, but it has this form. So now you have the unknown is a vector. The objective function is linear. And you have a constraint, which is that the polynomial function whose coefficients are defined by the vector, the unknown vector c, must have magnitude smaller than 1 at every point. And this is still infinite dimensional because the unknown c is finite dimensional, but the constraint is actually infinite dimensional. You have a constraint for each omega, each real number omega. However, this infinite dimensional constraint is semi-definite representable, so it can be reformulated as some condition involving a semi-definite matrix. And the main tool for this is the Fourier-Ries theorem. So I don't have the time to provide a full derivation, but just briefly, Fourier-Ries states that, so there is a, it's not exactly this, these degrees, but a degree n trigonometric polynomial p is non-negative if and only if it can be written as a sum of squares. So if and only if it can be written under this form. For some, actually, sum of squares with degree n/2. And using this, we can reflect. So first, we can rephrase the infinite dimensional constraint as the fact that some trigonometric polynomial must be non-negative. And so, thanks to the Fourier-Ries theorem, it's equivalent to the fact that the polynomial is sum of squares, and sum of squares polynomials can be represented as through semi-definite matrices. And so we do this, and we arrive at the following semi-definite program, which is equivalent to the original total variation minimization problem. So we still have the C unknown, and now we also, so instead of the constraint, which was infinite dimensional, we have something else which involves a matrix, such that some other matrix is semi-definite positive, and the matrix Z must satisfy some linear constraints. Sum diags is the operator which computes the sum of the coefficients along each diagonal. The matrix Z has dimension essentially n by n, where n is the number of measurements. So when the number of Diracs is small and the number of measurements is large, we must solve a high-dimensional problem to recover only a few Diracs. So it's computationally costly. Now what I'm going to present is something that we can try to do to avoid this dimensionality issue. It's to subsample the measurements. And so, as I told before, I'm going to explain why the TV minimization approach still works with subsampled measurements, but unfortunately, the dimension of the semi-definite program does not shrink. So subsampling the measurements simply means that we extract some set T of coefficients from the set of Fourier measurements, where ideally the number of elements in T is of order S, the number of Diracs, and we consider essentially the same estimator. We try to reconstruct the unknown measure by looking for the measure with the correct Fourier coefficients for all subsampled indices K and with minimal total variation norm. And provided that the set T has been chosen uniformly at random, so it has been shown. Actually, the results I show here is not can be refined, and it has been done notably by Clarisse Poon, Nicolas Keriven, and Gabriel Perret. You can show that if the cardinality of T is larger than the number of Diracs up to some logarithms, then the subsampled total variation minimization problem is still correct in the sense that its solution is still the ground truth unknown measure. And to derive a numerical solver for this subsampled TV minimization problem, we can still derive an equivalence with a semi-definite program. So the principle is exactly the same as without subsampling. We are first going to compute the dual problem and then apply Fourier. So this is with no subsampling, and with subsampling, not much changes. So here we have to keep only the subsampled coefficients. Here also the vector C must be sparse. So it must have non-zero coefficients except at indices in T. And in the resulting semi-definite program, also nothing changes except the fact that since so C is sparse, so it must be upsampled to come in this big matrix. But that's all. And in particular, you observe that the dimension of Z stays the same. And the key reason for this is that Fourier does not take advantage of sparsity. Indeed, the classical theorem tells that trigonometric polynomial is non-negative if and only if it's a sum of squares. And if the polynomial is sparse, maybe you could expect that the factors in the sum of squares decomposition are also sparse, but it's not true. When you know that the polynomial P, which is non-negative, is sparse, it doesn't really help. So this is why, as announced, subsampling does not make the SDP dimension small. However, it's possible to derive a small size SDP by subsampling or sketching the subsampled semi-definite program. And then we have the correct dimension. It scales the right way with the size of the set T. However, it's not exactly equivalent to the TV minimization problem. And this is what I'm going to tell now. So the idea to derive the sketched or subsampled semi-definite program is to imagine that the sparse Fourier theorem, which I said was not true, is true. So if we do this, we can perform the same derivation, and this time we arrive at a semi-definite program with a small size matrix Z. So if indeed the sparse Fourier theorem is true, then it's great, because our sketched semi-definite program, it's equivalent to TV minimization, so it enjoys the same correctness guarantees. And on the other hand, it has a moderate dimension, so it's easier to solve. But since sparse Fourier is not true, this equivalence may not be true. And indeed, there are some situations in which it is not true. The sketched semi-definite program and the TV minimization problem don't have the same solution. However, numerically, it seems that the sketched semi-definite program has essentially the same, provides essentially the same reconstruction quality as the non-sketched semi-definite program. So here you see, as a function of n, the total number of measurements, and cardinality of t, the number of subsampled measurements, the probability that the semi-definite program correctly recovers the unknown measure. So on the left-hand side, it's a subsampled but non-sketched case. And on the right-hand side, it's a sketched case. And you see that actually both programs seem to perform the same. So this yields the following conjecture. Under some technical assumptions, which I'm not going to describe in detail, the sketched semi-definite program is able to recover the ground truth measure. So it's something that we've been working on, not full-time, of course, but for years now. And it's a difficult problem, so we haven't a proof of the conjecture. Otherwise, I would haven't called it a conjecture. But by trying to prove this result, we wrote a small tool, which I'm going to present in the last minutes of my talk. It starts from the fact that in our proof strategy, we have to upper bound functions of this form. We have many functions which are integrals over one parameter of functions depending on several parameters. So the integral is still a function of several parameters, and we need to compute upper bounds. And we have many functions like this. So at the beginning, we wrote pages of computations, and then we realized it was actually possible to automatize the computation. So let me stress that what we want is not exact expressions for the integral. The functions that we have, they are sufficiently simple in some sense so that in theory it's possible to compute exact expressions for the integral. But they are too complicated for what we want to do. So here is, for instance, what Mathematica returns when you feed it a simplified version of the integral on the slide before. And so you see only the beginning of what of Mathematica's output, And you see, it's too complicated. What we want to do is to be able to compute the limit of the integral when this variable goes to this one, or when some parameter goes to infinity. With this expression, we can't do nothing. What we need is simple, but not exact upper bounds. And so to do this, we have defined a set of admissible functions, which are both simple, so that it's possible to compute integrals of admissible functions and upper bounds of integrals of admissible functions, and expressive, in the sense that all the functions that we're interested in are admissible, or at least have an admissible upper bound. And we implemented an algorithm to compute integrals and upper bounds of admissible functions. So I don't have the time to precisely explain what admissible functions are. Briefly, they are piecewise defined functions. And the pieces of the definition domain are chosen in a specific way so that it fits well with the type of functions that we have to represent in our computations. Actually, the pieces are represented by binary trees, so there is a relatively nice graphical representation of the definitions. And on each piece, the admissible functions, they are products of elementary functions, very simple elementary functions, with restrictions on which elementary functions you can use in each piece. And once you have defined admissible functions, the algorithm is relatively straightforward. First you have to upper bound each function you meet in an integral with an admissible function. Then, since each admissible function is piecewise defined and the integral is linear, you say that the integral, it's the sum of the integral on each subdomain. On each subdomain, the admissible function is very simple, so you can explicitly integrate. And then you sum the terms and you remove the ones which are smaller, and that's all. And for instance, for the integral in my first slide, the upper bound that is returned by the algorithm is as follows. So the binary trees, they represent the pieces of the definition domain. And on the right-hand side, it's the value, the expression of the upper bound on each piece of the definition domain. And you see that this expression is relatively simple in the sense that on each piece we have almost almost rational functions. It's easy to understand what happens, for instance, when x1 goes to x2 or when n goes to infinity. With this, I think I'm going to stop. Thank you for your attention.
Thanks. We have time for one or two questions. Maybe. I had a quick question about this statement that sketched SDP is not the. You can show that there are instances where it's not the same, doesn't give the same result as the non-sketched version. Is this per instance, or does it depend on the sketch? So if you form two different sketches, it's going to be true for both?
Actually, so I call the SDP sketched because actually the correct word for the SDP, I guess, would be subsampled, because the subsampling, it's not random like in I think what is usually called sketching. We subsample the semi-definite program using the same subsampling set as the measurement. So once we've fixed the subsampling set, there is only one sketched semi-definite program.
Yeah, I see. Okay, and then for any of these random subsamplings, a given program would not be equivalent to the unsketched version, or this depends on the choice of the sampling?
I think it depends on both the choice of the sampling set and the original measure.
Okay.
So for most measures and sampling sets with the proper sizes, the sketched SDP is equivalent to the original problem in the sense that they have the same solution, which is the correct measure. Right. But we have an explicit example of a situation where it's not equivalent, but it's for a very specific sampling set and also a particular measure.
Thanks. John?
I have a question if I have. Yeah, thanks. Very nice talk. So I have a question, maybe like a remark. So in these kind of problems, the idea that you have this maybe first method like this sketched SDP, to the extent that it can give you not the exact solution but a sufficiently a good enough estimate, couldn't then you plug it in with some gradient descent or gradient flow algorithm as a, just view your initial model as a warm start to then have a local method that just refines? Or, I mean, in a sense, what, is it very important to have, like, to solve the problem in just one step with a sketched SDP rather than with local methods?
I don't think it's so. In this case, most of the time, the SDP that we consider, their solution is exactly the right one. It's not an approximation of the right one, so we don't have to ask ourselves if we have to refine the solution. However, it's true that we could approximate the solution of the SDP with only a few iterations of a costly solver and then use a simpler optimization routine. I don't know if that would give, I don't know how this would compare to other super resolution algorithms. At the first slide, in the first slides of my talk, I mentioned the fact that there are several families of algorithms for super resolution problems. And there are already algorithms which mix convex steps and non-convex refinements. In particular, the sliding Frank-Wolf method. I don't know. Yeah, I don't know how they would compare, but it's somewhat in the same spirit.
Good. Well, let's thank you, Anne. Our time.